This is going to be homework 4, part B, in which we have a well-mixed tank, and our Q, we have a flow rate coming in and a concentration in that flow rate, and we're going to find equations for the height of the tank and the concentration of the liquid inside the tank. This has a lot of overlap from our first part of the homework, in which that finding the equation for the height is going to be the same, and we'll look at it as the changing mass of the system would be equal to our Q in minus our Q out, which in this case is AD times the square root of 2GH, and our Q in is just Q in. And we can represent our V as our AC times H. So we'll divide by AC on both sides, getting us dH over dt equals Qn minus our AD 2GH all over AC. And we can do that because normally this would be density in front of these. However, because it's an incompressible liquid, our densities will all be equal, meaning we can take them out of that part of the equation. Next, to find the equation for the changing rate of concentration, we're going to have to do something similar. So we can look at it like this. Our concentration will change at a rate of our concentration times our volume over dt, and we'll have our concentration times what's coming in, so our C in times our Q in minus our C out times our Q out. In this case, because we have a well mixed container, well mixed, our concentration going out will be equal to the concentration of the tank, which in this case will just be C. So our Q out will be the same as this equation, our AD times square root of 2GH, so we'll fix that. AD times 2GH. And now that we're here, we can do the same thing with our volume as we did before. So split it into AC and H and divide by AC. So we'll end up with CH, this all over AC. And then again, now we will do our product rule on this side of the equation to split up our DC and DH. So we get H times DC over dt plus C times C times DH over dt. And now we'll move our C times DH over here to this side, getting us minus C dH dt. And then we'll divide by H on both sides, or just 1 over H here. And that will get us our final equation for the changing concentration, because now our H and C dH dt on this side have been removed. So we just have this equation is equal to our dC dH. And you might notice this is still in here. However, we have what our dH dt in this case will be equal to. So we will just plug this in to find our final equation for dC dH. This is going to be homework 4, part B2. So we'll have all of our givens here, which have been wrote here. So firstly, we've imported our numpy, our scipy, integrate, solve by VP to solve our differential equations. and our plotly to make our subplots later on. So from our givens, obviously our gravitational constant, our initial flow rate in 0.1, and that will be increased by 10% or times 1.1 to give us our Q in, our cross-sectional area of 1 meter, and our the size of the hole at the bottom, 0.01 meters, and then our initial concentration coming in, and that will be increased by 25%, so 1.25 times our initial concentration. So the next thing is we'll need to get our initial concentration of the tank, which is easy. It will just be our initial concentration coming in, because that's just been flowing in the whole time, meaning the concentration in the tank should be what's been flowing in at a constant rate. And then our H0, which will be equal to the same thing it was for our part A. So we will have our Q in 0 squared divided by our AD squared, and that is multiplied by our 2 and times G, which should give us our H0. The next thing we'll do is set up how long we want our simulation to run. So we'll go 1,000 seconds, and our plot for plotting this out, and we'll do these as equally spaced points. So that'd be ln space, and that will be from 0 to our t end, and we'll have 1,000 different points. So that's all good. Next thing we need to do is make our function for our concentration and height. So we'll just do that as 1, combining them. So we'll define our dV dt, dV dt. Oh my gosh. I don't know why I'm blanking on this. As a function of t and v. And first thing we'll need to do is unpack our concentration and height into that v. Then we'll define our Q out, which in this case is just going to be our AD times 2 times G times H, square root of that, 0.5. Oh, hold on, that needs to go on the outside, 0.5. So now we have our Q out. So our dH dt will be equal to our Q in minus our Q out divided by the cross-sectional area. So that gives us our dH dt. And now we can get our change in concentration from the equation we derived in the first part. So we'll get our C in times our Q in minus our concentration times our Q out, because it's well mixed, meaning the concentration in the tank will be our concentration going out, divided by AC, and then minus our concentration again, times dH dt, and this all will be divided by H, and then from this we will return our dH dt. We have to do dC dt first and our dH dt second. So there we go. Now we'll use our IVP. So our results will be equal to solve IVP of our function. So dV dt. The range we want it to go on, so 0 to t end. Our initial values, which in this case are C0 and H0. We want our dense output equal to true. And for the sake of accuracy, our method will be radu. Not changing. Okay, I went back, checked real quick because I thought this didn't look right. This needs to have these in order to work correctly. So now we should be able to move on. All good. So CA and H will be equal to our res.sol for our t-plot, giving us the numbers for each one of those points. And then we'll move on to plot these out. So our fig make subplots rows equal 1, cos equal 2. And we'll move on, fig.add scatter. Our x will be our t-plot. Our y will be our CA. Our name for this will be CA. Mode will be lines. We'll put this in row 1, column 1, and we should be able to just take this and make this our height. Height, name H, lines, then row 1, column 2. And this CA is not defined. CA most certainly should be defined. And we end up with our concentration coming to the steady state at our new N concentration of 1.25, and our height ends up somewhere around the range of 6.1 with our 10% increase to the initial flow rate. All right.